Good morning, ladies and gentlemen. My name is Dr. S.M. Humani, and I'm going to be your lecturer for physical chemistry, SCHM or 4CHM 321. So, before I can proceed with this particular module, or before I can proceed with the topic for today, there are two important things that I want to start with. Okay, first of all, before we start with this module, I want you to make sure that each and every one of you are in possession of Atkins physical chemistry textbook. Majority of the stuff that I'm going to talk about, or even the very same notes that I'm going to present, they've been derived from Atkins physical chemistry textbooks. So if you don't have a textbook, but I do hope that all of you do have the textbooks, make sure that you have one. And secondly, so this particular course is basically a continuation of the course that we did on the second year level. Majority of the topics that we are going to introduce for this level will basically be just an enhancement of the topics that we did during the previous year. We'll talk about chemical equilibrium, we'll talk about the phase diagrams, and we'll also talk about electrochemist. So all those topics are all the topics that we actually covered last year. So if you still have the notes from the previous year, make sure that you do go through those notes in order for you to be able to understand this particular course much better. So like I said, ladies and gentlemen, for this particular chapter, we'll basically be looking at the principles of chemical equilibrium. But before I can talk about the principles of chemical equilibrium, so if we can recall about the topics that we basically did during the previous year, I think you'll remember that we touched about the principles of thermodynamics during the second year level. Among some topics that we spoke about the enthalpy. We also talked about the entropy of the system. And last but not least, we also talked about the Gibbs free energy. So all those topics, when we move through this particular chapter, I'll also say something about them. So if perhaps maybe you don't have a memory of them, I'll advise you to go back to the previous notes. So all those concepts that I've just mentioned, so if we can look properly, most of them are actually affected by whether temperature or pressure. But in this case, as you can see, at constant temperature and pressure, a reaction mixture tends to adjust its composition until its Gibbs energy is at the minimum. So what I'm trying to say is that, so when we are going to talk about the Gibbs energy, we are going to talk about the Gibbs energy at the constant temperature as well as the constant pressure. Because if the temperature is not constant, or neither the pressure is not constant, one can be able to get different values of Gibbs energy. The other thing that is very key around this chapter is that in thermodynamics, it can predict whether a reaction it has a tendency to form the products or not, but it says nothing about the rate of reaction. So we are going to look at different scenarios whereby we can try to have a relationship between thermodynamics or between the Gibbs energy as well as the rate of reaction. So if we know that particular relationship, there are a number of things that one can predict, like for example, whether our reaction, it will be spontaneous or it won't be spontaneous. And we can also predict whether our reaction will favor maybe the forward reaction or the backward reactions. So all these things, this is basically what this particular chapter is all about. So, ladies and gentlemen, let's look at the principles of chemical equilibrium. Okay, the first concept that I want us to introduce, or the definition, it is what we call the reaction Gibbs energy. So when we have a reaction, of course, we're going to have the Gibbs energy. But what is the reaction Gibbs energy? What is the significance of this energy? So by definition, we are saying that the reaction Gibbs energy is defined as the slope of the graph of Gibbs energy plotted against the extent of reaction. So in the next few slides, so we are going to see how to plot this particular graph. So if you are having maybe a question, or maybe you are having a reaction, one should be able to predict or to be able to calculate the reaction Gibbs energy. So if you are calculating the reaction Gibbs energy, perhaps from the graph, obviously you have to plot the graph, and from that particular graph you're going to take the slope of that graph. That is where the reaction Gibbs energy will be calculated. But why this reaction Gibbs energy is so important? The reaction Gibbs energy can express the spontaneity of a reaction at constant temperature as well as constant pressure. So look at this statement: constant temperature as well as constant pressure. So if you are provided with a statement, I think one has to look maybe at the keyword constant. If you know that you have a constant temperature or you have a constant pressure, so which means you can be able to calculate the reaction Gibbs energy from that particular graph. But in summary, if the value of the reaction Gibbs energy is less than 0, it means that the forward reaction will be spontaneous. If the value of the reaction Gibbs energy is greater than 0, it means that the reverse reaction will be spontaneous. However, if the value of the reaction Gibbs energy is equals to 0, it means that the reaction will be at equilibrium. So as you can see from these three statements, the importance of the reaction Gibbs energy. So if perhaps I'm asking you whether are we going to have a spontaneous reaction or non-spontaneous reaction, obviously if the value is either less or greater than 0, it is spontaneous. But spontaneously can favor the forward reaction, or the spontaneously it can also favor the reverse reaction. However, as we can see, if the value is equals to 0, it means that the reaction, it is at equilibrium. So when we talk about chemical equilibrium, we know that the rate of the forward reaction, it is equivalent to the rate of the backwards reaction. One question that one can ask himself or herself is that how does the graph of Gibbs energy versus the progression of reaction looks like? So this is how the graph looks like. So when you plot this graph, you plot the graph of the Gibbs energy along the y-axis, whereas you also plot this graph versus the extent of reaction or the progress of reaction, the progress of reactions along the x-axis. So along the x-axis, as you can see, we normally start with our pure reactants, and maybe after some time, when our reaction has finally reached completion, we'll have our pure products. For this kind of graphs, there are three types of graphs that can be achieved. As you can see, we have the reddish graph like A. We also have the brownish graph B, as well as the pinkish graph, which is graph C. What does these three different graphs tell us? So when we look at graph A, so when we start with the pure reactants, as we can see, with an increase in the progress of reaction and the Gibbs energy, you can see that this graph, it will continue increasing up to infinity. So in other words, we normally say that this particular kind of reaction, they do not necessarily go to completion unless perhaps maybe you stop the reaction. Like for example, like if you are manufacturing like the plastics, it really depends because the plastics or the polymers, they can have maybe different a number of monomers up to maybe 1,000. So I was saying up to 1,000 or even a million, unless you terminate the reaction, it's hardly not easy for those reactions to reach completion. And we also have the reaction that can go to completion. So when you look at the graph of C, when you start with the reactants, maybe in this particular point, with an increase with the extent of reaction, we are going to reach a point whereby all the reactants, they have been converted into the product. So graph C, it goes to completion. However, when you look at graph B, with the graph B, we say that the graph B is equilibrium with amount of reactants as well as the amount of the products. So this particular graph, initially, as you can see, it will decrease with an increase with the reactants or the progress of reaction until it reaches a point B. So at this point B, we say that the number of reactants, it is at equilibrium with the number of products, and from there our graph will also coincide. For chemical equilibrium, or for this particular chapter, as you can hear the name chemical equilibrium, we are basically going to work with the graph that can reach equilibrium, like graph number B. So going back to the reaction Gibbs energy. So by calculations, or in terms of the equation, the reaction Gibbs energy is equals to delta G divided by delta N. But for us to have delta G as well as delta N, N can be the number of moles. It means we need to have this particular graph. The change in the Gibbs energy divided by the change in the number of moles. But by the definition, we say the reaction Gibbs energy is the difference of the chemical potentials of the products and reactants and the composition of the reaction mixture. One thing that we must also recognize is that the reaction Gibbs energy is the slope of the graph of the change in G versus the composition of the system. Is whereby we are saying the reaction Gibbs energy is equals to delta G divided by delta N. But for us to use this equation, it simply means that we need to have a graph, and from our graph we're going to take two values of G, and as well as we need to know what are our reactants. If you know our reactants, we can be able to use this equation to calculate. But if our reaction Gibbs energy is at equilibrium, at constant temperature and pressure, we are going to say Rg is equals to 0. But if we know the equilibrium constant, we can also calculate the reaction Gibbs energy by using this equation. Reaction Gibbs energy is equals to minus RT, the ln of K. So what about the instances whereby we don't have the equilibrium constant, rather we have the equilibrium quotient? So even when we have the equilibrium quotient, we are still going to do the very same thing. To calculate Q will be calculated as the multiple of the product divided by the multiple of the reactants raised to their coefficient according to this equation. However, the formula that will be used in these instances, it will be this equation. I think others perhaps they can say what's the difference between Rg as well as this R with this particular R. There is no minor difference, just that in these instances it means that we don't necessarily have constant temperature as well as constant pressure. So since we don't have those things, we can't necessarily say perhaps this value is equals to 0. This one is the actual value that will be calculated, whereas this one is the arbitrary value. Okay, just moving forward. So when we have the equilibrium constant, remember the formula is equals to 0 is equals to the reaction equilibrium, the reaction Gibbs energy plus RT ln K, whereby the formula that I said we must use is Rg is equals to minus RT ln K. So we can use the values of Rg from a data table to predict the equilibrium constant. And we can also measure K of Rg reaction and calculate Rg. I think this slide is basically repeating what I've said. So if we know Rg, it means we can calculate the value of K. Or even if we know K, we are also be able to calculate the value of the reaction Gibbs. Ladies and gentlemen, since we know that the reaction Gibbs energy is equals to minus RT, the ln of K, let us not forget that R is a gas constant, and temperature in this particular instance, it will be constant. What about the reaction Gibbs energy as well as K? It means that we do have the relationship between the two. So if we have the relationship between the two, what does that particular relationship tells us? So if Rg is equals to minus RT, the ln of K, what about K? It means that the ln K will be equals to minus Rg divided by RT. So if the value of reaction Gibbs energy is less than 0, then the value of K will be greater than 1 and the products will predominate at the equilibrium. But if we want to summarize this particular slide, so using the graph on the right hand side, so when you look at this particular graph, we can see that when the value of K is greater than 1, if the value of K is greater than 1, it means that the reaction Gibbs energy, it will be less than 0. So even if we can put the values or like on one of the equation here, as long as the value of K is greater than 1, the value of G will be less than 0. And if it is less than 0, we remember that our equation will be spontaneous, and if it is spontaneous, it will favor the forward reaction. If the value of K is equals to 1, if it is equals to 1, it means that the value of Rg will be equals to 0. I think that one, perhaps we can try to put the ln of 1 in this equation. So when we put the ln of 1 in that equation, I guess so the ln of 1, basically it is equals to 0. If you say 0 multiplied by RT, which means this Rg will be equals to 0. So if K is equals to 1, it means that our equation, it is at equilibrium. If the value of K is less than 1, it means delta Rg will be greater than 0. The value of K as well as the value of reaction Gibbs energy, they basically tell us more or less the same information. Remember that they can tell us whether the reaction it is spontaneous or it is not spontaneous. It can tell us whether the reaction it is at equilibrium or it is not at equilibrium. So even if it is spontaneous, so these two values, they can also tell us whether the reaction is going forward or is going backwards. So still talking about the relationship between the reaction Gibbs energy as well as the equilibrium constant, there are also some points that we must also take into consideration. If the reaction Gibbs energy is greater than 0, it means then the value of equilibrium constant is less than 1, and the reactants will predominate at equilibrium, which means this particular reaction, it will favor the formation of the product. And this reaction is not thermodynamically feasible. However, the products will predominate over the reactions significantly only if the value of K it is much higher, is greater than 1. But even with a lower value of K, you may have the product formed in some reaction. So even if the products have been formed in these reactions, the reactions will still predominate. So these are some of the instances where we can see now what is happening. So in a nutshell, if you want to summarize this slide simply say that if the value of K is less than 1, the reactants will predominate at equilibrium, right? And this reaction will not be thermodynamically feasible. However, it will still be possible. Okay, still talking about the relationship between the reaction Gibbs energy as well as the equilibrium constant. Remember that when we have the reaction, we can have the endothermic reaction and you can also have the exothermic reaction. The endothermic reactions are those reactions that normally absorb heat from the atmosphere. So when you talk about an instance in this case whereby you are having an endothermic reaction, so so if you want the value of the reaction Gibbs energy to be less than 0, so for this condition to be possible, it means that the entropy of that particular system, it must be greater than 0. So its temperature must be high enough for its T change in the entropy to be greater than the enthalpy of that reaction. So the switch from the reaction Gibbs energy greater than 0 to reaction Gibbs energy less than 0, it corresponds to the switch from the equilibrium constant is less than 1 to the equilibrium constant is greater than 1. So this switch, it normally takes place at a temperature at which the reaction enthalpy minus T delta entropy is equals to 0. Or we can say that temperature is equals to the enthalpy divided by entropy. I don't think that you are quite maybe shocked or surprised to see this equation. This equation, like I said, that you have to go back to maybe the second law of thermodynamics, whereby it is talking about the relationship between enthalpy as well as the relationship between the entropy. Enthalpy is given by the letter H, while the entropy of the system by the letter S. So look at these two things carefully, and if you can look at them carefully, you'll know how this equation was derived. So when we look at the thermodynamic criteria of spontaneous, so in this case, I'm going to look at the Gibbs equation, whereby it summarizes the relationship between the Gibbs energy, the enthalpy, as well as the entropy of the system. Remember that the equation we say delta G is equals to delta H minus T delta S. From this equation, there are a number of factors that one can be able to summarize if we still want to look at the relationship between reaction Gibbs energy as well as the equilibrium constant of the reaction. So the first scenario, we say that if the reaction is exothermic, if it is exothermic, we know that for exothermic reaction, it means delta H is less than 0. So if it is exothermic and the entropy of the system is greater than 0, it means that delta G should be less than 0 and K should be greater than 1 at all the temperatures. If the reaction is exothermic and the entropy is less than 1, remember for the previous statement, we are saying that the entropy is greater than 0, whereas here the entropy is less than 0. It means that delta G is less than 0 and K is greater than 1, provided that temperature is less than what? Is less than the change in enthalpy divided by the change in the entropy. I think others, ladies and gentlemen, you can look at them. And also do consult your textbook, because this is just a summary. So moreover, still talking about the criteria of spontaneity, looking at table 7.1, we said that delta G is equals to delta H minus temperature, the change in entropy, delta S. So what about when we have endothermic? For endothermic, we know that when we have an endothermic reaction, it means that the value of H, it should be greater than 0. So, and the value of entropy should be less than 0. So in this case, delta G should be less than 0 and K should be greater than 1 at no temperature. Or if delta H is positive and delta S is negative, delta G will always be positive regardless of the temperature. So these statements are basically say the same thing. So, so this slide is still talking about the criteria of spontaneity. I don't think there is anything new regarding this particular slide. Still talking about the relationship between delta H, delta S, and delta G, and what's gonna happen if maybe delta H is negative, delta S is positive, and all that particular stuff. You can look at the slide. So what about the factor that will affect perhaps maybe the sign of reaction Gibbs energy? So let's look at different instances. There are those instances whereby the value of enthalpy is positive and the value of delta S is positive. So in this case, it means that the reaction will proceed spontaneously at higher temperature. At low temperature, the reaction is spontaneous in the reverse direction. So what I'm trying to say that if you have the value of G, H, and S being positive, both of them, it means that we do have spontaneous high temperature and at low temperature, reverse direction. So if the value of H is positive and the value of delta S is negative, as you can see, this one is negative. Negative by negative, it will be positive. So in other words, the value of delta G will also be positive. So in other words, delta G will always be positive. The reaction in the spontaneous in the reverse directions at all temperature. It means that that reaction will be reversed at all temperature. What about the instance whereby the value of H is negative, the value of delta S is positive? Delta G is always negative in this case. It means that the reaction will proceed spontaneously at all temperature. The last instance is whereby the value of H is negative as well as the value of delta S is negative. So in that instance, the reaction will proceed spontaneously at low temperature. At high temperature, the reverse reaction becomes spontaneous. Okay, before I wrap up